This video we are going to look at surface tension from an engineering perspective. Imagine you've got a glass of water, and this glass of water is obviously going to have lots and lots of molecules of H2O in there, right? So imagine that this is what these molecules look like. That you've got molecules at the surface, and then you've got molecules internally as well. The molecules that are under the surface, they're being attracted to each other in a balanced manner on all sides. So they're being held in their positions, right? Whereas the molecules that are at the top, they're only being held in their place by the molecules that are next to them, or let's say the molecules that are under them if we're looking at the plane. So because of that, because the forces are not balanced for the molecules that are at the top, they're going to start developing stronger bonds between each other, okay, at the surface. And this is something that is called cohesion. So the molecules at the top, at the surface, are going to develop stronger bonds among them, and that is going to give them a hypothetical membrane kind of situation is happening here, okay? Hypothetical membrane, a hypothetical skin forms, you could say. So now that if you were to apply a force on top of them, say you were putting a paper clip on top of this water surface, it's going to stay up here. It's going to feel like it's floating up here, but it's actually not floating. It's being held up there by these water molecules on the surface. If you were to put a needle on top of it, very, very gently though, you're going to see that it's going to stay on top of the water surface. You could have also heard about the phenomena where insects crawl on top of water. That is what they're using. What they're using is the phenomena of surface tension. Okay. These stronger bonds between these molecules at the surface give them the ability to hold a certain weight on top of the surface. And if you were to apply a pressure or a force on top of the needle or on top of the paper clip, it's going to sink. So what you could say is that this hypothetical membrane or skin that is formed, this is kind of a tensile force that is acting on the surface, okay? And that's where surface tension gets its name from as well, that this tensile force is acting on the surface, so surface tension. And it's usually represented by the symbol sigma, surface tension. And the SI units of surface tension are Newton per meter. So the official definition of surface tension is that the intensity of the molecular attraction per unit length along any line in the surface. What you should remember is that this membrane or skin, it's hypothetical, okay? The surface only behaves in this way. There is no actual membrane present or an actual skin that is present on top of the surface. No, that doesn't happen. This is just a conceptual analogy that makes it easier for us to understand what surface tension is. And another thing that you should remember is that surface tension occurs at the interface between two fluids that cannot mix with each other. So in this case, those fluids are liquid, which is water, and air, which can be considered as a gas. Okay. So surface tension is responsible for a paperclip staying on top of the surface, a needle staying on the top of the surface, but other than that as well, the air bubbles developing into a liquid, that's also because of surface tension. The water droplets, for example, being spherical, that's also because of surface tension. So if you were to look at the water droplet, why is it spherical? Why is it not of any other shape? The reason for that is also surface tension. And how is that? So if you were looking at this water droplet and you cut it in half, okay, and you cut it in half, and then you look at this water droplet now, the what you will see is that the force that is developed around the edges of this water droplet is because of surface tension. So we're going to look at the circumference of this water droplet cut in half. The circumference is 2 pi r. Okay, 2 pi r. And because surface tension is responsible for the force that develops here, so it's going to be multiplied by surface tension, sigma. And now to balance this force, it's going to be balanced by the pressure difference that is acting over this circular area. And the circular area, we know that the area for the circle is pi r squared. So pi r squared multiplied by delta p. Delta p over here is equal to pi minus pe, where pi is the internal pressure and pe is the external pressure. Okay, so for equilibrium to hold, they should be equal to each other, and from here you can simplify this into this equation, where again pi is the internal pressure and pe is the external pressure. So what does this equation tell you? What this tells you is that the pressure inside the drop is greater than the pressure surrounding the drop. Why is that? Because if you take PE onto the other side, PI is going to be equal to PE plus another term here, right? Which means that PI is most definitely going to be greater than PE. So what does that result mean? The pressure inside the drop is greater than the pressure surrounding the drop. And now because of that, because the pressure inside is greater than the pressure outside the drop, this water droplet is going to take the form of a sphere.